Welcome to this session. So we are going to discuss to state and prove some different methods of finding residues of functions. So the first one, A, let's discuss about how we find residue of or at simple poles. Residue at simple poles. So the first thing we want to discuss residue at simple pole Z equals to A So the statement is that if f of z has a simple pole at z equals to A, then residue of the function at A is given by limit as z approaches A of z minus A multiplied by the function f of z. So this is the definition. So quickly, let's see how we prove this. So proof. So let f of z be given by a naught plus a1 into z minus a plus a2 into z minus a squared. Because the simple pole is at z equals to 1, then this formula will stop at this point as per the Lorentz series, which implies that you can multiply every term by z minus a, and we have z minus a multiplied by f of z will be given by a naught into z minus a plus a1 z minus a, because remember this one is multiplying every term, so now the power of this one will be 2 plus a2 z minus a power 3 plus up to the last term b1. So which implies making b1 the subject, will get z minus a times f of z, and then you subtract these other terms, minus a naught into z minus a plus a1 into z minus a squared plus a2 z minus a power 3 plus other several terms. So that's what you'll have. Now taking limits, as z tends to a, we have limit b1 is equals to limit as z approaches a of z minus a times f of z. So that's what we'll have, because all these other parts will be 0. So this square bracket. So this is the limit of this other part. So hence by definition, residue is actually just B1. So residue at z equals to A is given by limit as z approaches A, z minus A, f of z. So this is the proof of that given formula. And then case 2, sometimes we may have a simple pole, but the function is rational form. So 2, if f of z is of the form f of z equals to over where when you put a in the denominator, you get 0, but when you put a in the numerator, you get non-zero value. Then residue at z equals to a is given by the numerator at a, and then you differentiate the denominator and put the value of a. So this is also another way of finding residue at simple pole z equals to a, but this you use it when a function f of z is rational function. So proof of this, so residue at z equals to a is given by limit as z approaches a, z minus a times f of z. This by definition, we have just stated in the first case. So this by definition, given in Roman 1. So this we can write it as limit as z approaches a of z minus a. You multiply this function now is of the form phi of z over psi of z. This is the structure of the function f of z. So by Taylor's theorem, we have that the residue at z equals to a will be limit as z approaches a. Now we write this part as z minus a, you multiply by phi at a plus z minus a times phi prime at a, and then plus other terms. And then, so remember this now, we divide this one by at a plus z minus a, derivative at a plus other several terms. So we do both for the numerator and denominator. So which will be the same as limit as z approaches a of Z minus A into phi at A plus Z minus A phi prime at A plus other several terms divided by Z minus A phi prime at A. Then we can even write the second term in the Taylor's expansion over 2 factorial, second derivative at A, and then plus other terms. So we are neglecting this one because we have been told that the denominator, value of the denominator function at A is 0. So that's why this is the same as this one, because this part is already 0. So that reduces to, i.e., residue at Z equals to A will be limit Z approaches A of, now, you see this Z minus A can be factored out and then cross out. So we'll have phi at A plus Z minus A phi prime at A plus other terms. And now when you factor out Z minus A in these denominator terms, it will factor out, it will cross with this Z minus A. So the first term in the denominator will be phi psi prime of A at plus Z minus A over 2 factorial, because 1 has been factored out to cross with this one. So we just have 1 power 1. Second derivative at A, then plus other several terms, which is simply the definition of residue at Z equals to A is given by phi at A over this denominator prime at A. Because when Z approaches A, this term would be 0 and subsequent terms will be 0. Similarly, this will be 0, other terms will be 0. So just remain the numerator, this, and this will be the term in the denominator. So this is how we find the residue for function f of Z at the pole Z equals to A, when the function can be written in the form phi of x, phi of Z over psi of Z. So this is the formula. In the next session, we give another method of finding residues and also provide the proof. Thank you.